excited to have today's speaker, Ito, joining us. Actually, Ito is currently here at the professors, and I think if you're excited about what he's going to talk about, wander out. So that's cool. Try to read it. So Ito is a visiting professor from Technion in Israel. And he has done a lot of fundamental work at the intersection of quantum optics and also physics of electrons, physics of nonlinear optical systems, and has received numerous awards all the way back to his PhD. He has a dissertation award, Bolatnik award, as well as more in here. So very excited to get started.
Thanks, Amir. Actually, I've been here now for a month and a bit on sabbatical, and I'm already recognizing some faces. Had a chance to give some talks before, and I'm happy to. I decided to go on something completely different and go with you into quantum areas that I find interesting. But basically, yes, I'm from Technion, sabbatical, and I think I'll use today to take you with me on kind of journey that on a field that is accelerating super fast, which we call strong field quantum optics, or generally into domains where we start finding quantum effects in areas that are not traditionally considered as part of the quantum fields. I'm also doing some lab tours tomorrow, and it's seeing some of the established areas of quantum, like Twizzler array, circuit QED. Those are the platforms where we know a lot of the most successful quantum experiments are happening. I'm especially interested in recent years in where quantum is not supposed to be working, areas that are not supposed to behave in quantum manner and still do for some surprising reasons. And I want to discuss one of them today at depth. So before I do that, just for, I want to bring one slide that is kind of trivial, but it's maybe to orient where I am in the bigger picture of quantum, and maybe more relevant for the younger students here. Because, when we think about quantum, especially on the frontier of computing, typically people consider which type of domain, right, you place yourself in. Is it the superconducting, trapped ions, photonics, now Twizzler arrays? Can argue whether others are promising or not, but I like to think about this as a 3D matrix of what we actually need to decide when we point at a particular platform for quantum computing. Right? It's not just what's the physical implementation, right? There is another aspect to it, which is kind of the computation method. Do we design for the gate-based, which is more similar to classical computers in some sense, or do the measurement-based? Those familiar with the classic sets and other ideas, but there is a third dimension to it that people don't often appreciate. Anyone has a guess, actually? What is the third dimension of, like, conceptually, when I try to orient different approaches for quantum computing? What is the third axis that you would be worth describing here? So I think many would be familiar with this, but maybe not be able to guess. If I think about the way we encode actual information on a quantum computer, right? It's very common for most people to assume we do this on qubits, but it does not have to be. Hilbert states that other than 1 or 2 level systems are also relevant. And I like actually to help kind of understand what I mean by this 3D matrix. If you think about the famous platforms for computing these days, IBM or Google will be on the superconducting gate-based qubits, right? And the default seen by you read the news. But other companies like Alice Bob, I think the biggest French company one of these days, will be also doing superconducting gate-based, but they will actually try to encode their qubits on continuous variable on the computer. So the basic Hilbert space for encoding the qubit is not a 2-level system, but harmonic oscillator. It's the photon that is the one holding the quantum information and not the fermion, if you like. right? And in similar ways, Amazon actually played on multiple fronts, but they had some really impressive publications this year that are also playing on that domain with continuous variables. Quantum, here, Xanadu are two biggest companies doing photonics in the domain, but are actually playing two different options here. From when do we want to encode photons on an analog two-level system, qubit on an analog two-level system with photons, where the photon goes, and we get dual rail involved. It's great, but Xanadu are actually publishing continuous variable types of encoding. And with this, I think it's worth thinking about quantum in this three-dimensional sense. And to locate myself, so I find this area really interesting. The idea that quantum information can be encoded on a bunch of different liquid spaces, especially larger ones with two-level systems. Then it gives a lot of options, especially for other function codes. So those curious about this, I'm also happy to discuss separate from today. We did some work on developing bosonic codes. Ideas like implementing GKP codes, those who heard about web calculus scale, and other systems along those lines. And I'm not going to talk about computing today, but I do want to talk about areas of quantum that are related to the photon, the harmonic oscillator, and see what we can do in those domains. And well, that's where I'm headed today. Generally, people interested in this area, I think there is a lot more potential. In some sense, it feels like we already know all possible platforms for encoding quantum information. So it could be like the fifth really promising one here. Until a few years ago, no one was putting this as a leading candidate, right? And now it seems like an obvious, some would argue, winner, right? So that's quite an interesting domain, and I think that in that sense, looking for platforms that encode quantum information from bizarre liquid spaces, also weirder than the harmonic oscillator, is still a place where we can find surprising things to do. That's where, I mean, it's not as heavily studied, and I want to, in that sense, talk about a few, right? When we think about what are the fundamental quantum systems, we normally thinking about a two-level system or a harmonic oscillator, right? The Technion and boson. But actually, there's a third candidate that is worth thinking about. When we think about free electrons, and there are some groups here in Stanford doing interesting work on this, like Mark Astovich or Olaf Solgardi and Stucker, having works that relate to what can you do in the free electron, all the free electron, and try to encode quantum information on that. And what's beautiful fundamentally about it is that it is a different liquid space than the conventional ones. It is a system that can be thought of as a ladder of energy levels, but where the bottom is so far away, you can think about it as double leak infinite. Much of what we do these days is mapping ourselves to interactions between those different systems. A lot of what we think about is conventional quantum platform systems will be interactions between harmonic oscillator systems. James Cummings and Technion is an example. So you should ask what will actually happen if we have a third system? What will be physics that we can explore when putting those two systems to interact with one another, or those two? So if you want another fun example, there is an experiment by Jelena Vukovic with other people here that was looking into the interaction between the free electron and the two-level system. It's based on a theory work we've done in 2021. And now the first experiments towards this is actually done here in Stanford with some signatures from a few months ago on archive. So this is, I think, a pretty interesting domain as what other types of quantum systems can be useful. And that's, if you want to read more about this idea of bringing the free electron as another quantum particle. We now call this free electron quantum optics in broad sense. There's a prospective paper we wrote earlier this year. There's also other contributors from the community, including us writing a roadmap about it. So this is getting quite interesting with more players in different domains. And I brought this as an example because I think the electron shows it's kind of a surprising quantum feature in the following sense that the electrons we work with when we do actual experiments with them, electrons in electron microscopes are typically moving at something between 1/2 to 2/3 the speed of light. For people coming from the slack cities, this is super slow. But still, already for us, it is a relativistic picture. And it's not very common to find physics systems where speed of light matters at the same time where we actually care about h-bar. In that sense, the electron is not seen as a natural creature where quantum effects should be easy to access, right? And that got me, kind of generalizing now about my group. I like this idea that quantum effects appear in unexpected places. For the electron, it's the result of spectroscopy with electrons being so accurate that despite being super energetic particles that are moving at a relativistic speed, we can still see changes in energy of individual photons being emitted or absorbed. And then that's the fundamental reason we can really see quantum effects with electrons, right? We can play on the coherence of electrons. But there are other places in physics, more broadly, that also have quantum healing in unexpected ways. One example of it would be in the X-ray domain. Why could we actually make entangled X-rays or squeeze sources of X-rays? This is one of those holy grails of physics. Quantum sensing with X-rays could be really valuable. Imagine that you have CT scans or other types of Röntgen scans of our body with squeezed X-rays, reducing dose there. But it's a holy grail. There are no good solutions for this right now. This is so in that sense, the domain where I want to take our talk today is in the context of intense fields. When we think about quantum optics, we typically imagine fields that are quite quick. Talk about individual photons, entangled pairs. But how much of quantum could still be relevant and interesting when we go to really intense sources of light, like the domains of light intensities we can see with our eyes. And that's the area we call strong field quantum optics. That's where I'm headed for the rest of today. Okay, for orienting ourselves. So strong field quantum optics and why go there? The kind of thinking there is, I mean, how far can we push entanglements and behaviors like this to explain? We think about attosecond time scales, for example, super short time scales, or extreme frequencies, but X-ray is an example. Or you can think about it from the other way. Like if we have experiments that are more and more people now doing strong field optics in combination with condensed matter systems, it's a way to drive phenomena based on conditions that are transient. Then how much can we learn actually from looking at light emission from very complex condensed matter systems? Maybe learn something about those systems. And that's so as a probing method of complex systems, or as a way to create quantumness on light, and two broad directions there. The thing about it is quantum optics at the extent. It's, I think, important to say upfront that it's an area that we should be a little bit lower our expectations about. The level of beautiful many-body entangled systems that people can build in established platforms of quantum, we are not expecting to go there so quickly. Those systems of extreme light are pretty dirty. So there will be very so shallow expectations, and I'll actually talk about what we can and what we cannot achieve. Right. So now, an example scenario to keep in mind, right? And that may be one of the most famous nowadays in extreme optics and extreme nonlinear optics. If we have a gas, it could also be liquid or solid, a gas that we glide it with some field, right? We know that there will be some complex dynamics of electrons inside. And those electrons that will be moving under the effect of the field will then radiate back out, right? To potentially radiate multiple harmonics of the field. Right. Now, over quite a few years, people were asking us, how do we control this process by controlling the fields coming in? For example, change the polarization of the field, encode that field with complex superpositions of light. And in some sense, quantum optics already provides us an interesting point of view that we don't necessarily need to change light classical properties, like superposition of colors, directions, polarization. We can also try to change the photostatistics of light. And that's an important thing to remember for someone who's coming from the classical optics perspective, that once we know the intensity of light, direction, A vector, right, the polarization, it's still not everything. Right? For the same average intensity, we can have multiple types of photon statistics. For squeezed light, squeezed amplitude, squeezed phase. And one of the earliest questions we were asking is how is the photon statistics of light going to alter the interaction it has with matter? And if you want to, there is a talk I gave as an optical webinar a year ago. It is broader about those aspects. Today, I'll try to also take you through quite a lot happened actually over the years since this community got quite out. So I'll try to also show you some of the most recent things that happened. If you want more detail, that you can take a look over there. So when thinking about this from the point of view of intense light and nonlinear optics, there are a bunch of acronyms that are quite famous in nonlinear optics. From second harmonic generation, where it's multiplying the frequency of light, or some frequency generation, pure nonlinearity, all of those were studied over decades. And in some sense, it's interesting to us, what would happen if you drive all those processes with light based on quantum properties? How would that change? And maybe the most famous of them nowadays, we had Anne Lulier, Nobel laureate, visiting us a week and a half ago, like this. And that was this is the domain for which she got a Nobel Prize, and she was the first to suggest that potentially a strong field could cause an emergence of a very large number of harmonics, the very non-perturbative manner, taking optics into this really extreme domain. And that is today considered an extreme non-perturbative regime of nonlinear optics. So maybe I'm not sure if everyone is familiar with this. So just a few words about that. What's the famous effect on the field she pioneered? But this is the idea that in some domains where the light intensity is strong enough, we should not think about the creation of harmonics perturbative effect anymore. Like for many decades, nonlinear optics was assumed, but you can actually extract and understand that there is suddenly a plateau of harmonics that is created. And that is because the dynamics of electrons is becoming a dominant thing. There is this idea that Paul Corcom initiated with three-step model, how we imagine nonlinear optics behave. There is a potential typically of the atoms that, since this field is so strong, is actually modified. And then the electron wave function that is trapped inside, there is a chance of flying out and leaking out to some extent at least. Since then, the field is oscillating so quickly, it's an optical field, it will actually be tilting it back, and then the wave function will be able to propagate back. Now, this is already, in some sense, a quantum description of what's happening there on the level of the electron. But the light is still treated as just potential. It's a classical field. That's a typical thing to consider. And what I'm going to jump into over the next slides is asking what happens when both light and matter behave in a quantum way, what it does. Okay, so just for context, there is quite a broad community asking questions about this interface, quantum optics, the explained domain. I guess you would not be super surprised because it's kind of a marriage of two Nobel Prizes. In the optics domain, we had this with 2 years in a row optics prizes for entanglement and quantum optics in 2022, and then for AGG in 2023. So for my defense, we were thinking about this long before it got into this kind of double Nobel thing for many good reasons. But it's not surprising that since around 2022, 2023, it got super hot. And I want to kind of show you a bit of the foundations what led to this and where we stand today. For context from Technion side, I joined Technion in 2018, and Owen Cohen, first guy in Israel to do a high-harmonic generation. And for me, it was also a mentor. So I actually stepped into this domain as a faculty member already, went into a new field to learn high-harmonic generation and asked how do we actually explain all of this with quantum optics perspective. And then Michael Kruger joined Pavlos Sidorenko as newer faculty members, but he second was my PhD advisor. And now in the Solid State Institute at the Technion, we have multiple labs and kind of a kibbutz version of the lab with students moving between labs and doing experiments in multiple places. Let's say it's my student who really started this, the theory of quantum harmonic generation. And Matan is foreign student. Now the one leading much of the theory and even moved to experiments. And Michael Beard is the first to do experiments on Price-Fuse vacuum that I'll tell you a bit later. Joel Fien is my Kruger's student, a postdoc. And there are now more and more students joining into this. For a broader picture, we now have collaborators with Andrea Pizzi in Cambridge. And works with us on theory there, and Nicky Vera started in Cornell actually, and did this. Recently, Maria Chefova, I'll mention later from Erlangen, is the first to show experimentally quantum light in very, very high intensities. And these are both collaborators on this. Peter Romanov, so moving to LMU soon, doing some of the experiments we were talking about. There is a really good, strong group, of double group, Olga and Misha, even though do TOE of those domains and are also studying this area. Jamison was now here with a LMS postdoc. Marin was my postdoc advisor. Actually, also stepped into quantum harmonic generation. I mentioned one paper that he led. Really beautiful work. And most recently, Weitzman, Yuri Tudovic, built another setup that is doing quantum harmonic generation. So all of those are different people that joined the larger collaboration that we're now doing on this. And I want to show you some of the recent stuff down there over the next half hour or so. But before I tell about the most recent stuff, I want to say something about foundations, like this marriage of strong field and quantum optics. And that is something that always bothered me. As you know, we teach in fundamental electromagnetism about how matter radiates. And we actually have those two ways to explain radiation that we teach in different courses, and we don't often put on the same grounds. If we think about the radiation by an antenna, right, like stuff we have in our phones, we typically describe this as a dipole radiation. But when we think about the atoms radiating, it will be a two-level system kind of emission, and that will be spontaneous emission kind of physics. And so we'll do Fermi vulnerable for that. So in a sense, this is Maxwell's equations in a neutral potential. Well, this will be Fermi vulnerable on QED. On one side, we'll typically have classical Hamiltonian that is potentially time dependent. This is the emitter. But on the other one, we'll have the Hertz operators for describing what's happening. On that side, we'll use formulas like this one. There is a radiating dipole, right? So we know how much energy spectrum. But the other one will be matrix elements, and then Fermi vulnerable. But even when we have a quantum metal, right, which is actually quite common in this still fits under this called semi-classical emitter. We can write a Schrödinger equation for the evolution under classical Hamiltonian. Classical in the sense of time dependent relations to the field is classical, but the wave function evolves in a way that is like Schrödinger type equation. And then we still calculate D, some expectation value, and stick it over here. In that sense, the theory of high harmonic generation, as an example, and all of the rest of nonlinear optics still fits on that side. So now, what the first thing we did in this field is ask actually what is the joint, what is a single theory that will explain spontaneous emission, dipole radiation, and then also high harmonic generation, and that is possible to do. In this paper, you want to read something that I think is still the best introduction to the field. And what we followed is a procedure you can see in multiple places. For example, Tanucci's book, Quantum, will have if you take a very complex initial state of quantum Hamiltonian, full quantum, but then you have a very strong field. So you are suddenly stuck with 10 to the 13 photons. How do you actually handle Hilbert space that is so big? So there is a procedure, a unitary transformation one can do when the initial state is a coherent state. Talk about beyond this soon. Then if there is a unitary transformation that will allow you to transform this Hamiltonian to something that is both quantized and time dependent. Feels like a bad idea, but it's not. The actual Hilbert space is much smaller because you get rid of most of the photons into the time dependence of the Hamiltonian, and that lets you solve something that is a much larger, much smaller space, which you can apply perturbation theory on, and then look into a variant of Fermi-Golden rule, describe them. And eventually lets you describe something that gives you the emission. That kind of picture captures everything. Captures both spontaneous emission, Fermi-Golden dynamics, spontaneous emission from time-driven system. You could basically also capture harmonic generation and then ask what will be the quantum state of light data. For example, do we get squeezing naturally from harmonic generation? Questions of that type would all be captured on this domain. and are now being studied by Tanya Cruz. Talk about this later on. So in a sense, coming back to this, we can describe and ask what is the quantum state that is created in those types of systems, even if they are strongly driven. That's kind of the foundation for much of what's coming next. So now I think it's worthy to kind of look into this fact in particular, because in some way it is the one that is now getting a lot of attention in the community, but for a good reason, I think. It's a place where the physics is not intuitive. It's not easy to describe it by some kind of perturbation approach. And that's an area that is, for this reason, most interesting to try to do in quantum manner. And for this, what is, I think, now the hottest topic in the field to look by experimental efforts being done, including here, the personal field Box-Farm's group, from the lab is also building something along those lines. Is what happens when we try to drive processes that are strongly non-perturbative in optics by using quantum lines as the bypass. And that will be, if you want to try to imagine it for a moment before we go into more formalism there. In a sense, the molecular dynamics I was also describing before, it's what we call the three-step model, is the scenario of ionization, acceleration, and recombination that one could also study with a wave function evolving and then interfering back, still under a classical field. And in that sense, once quantum light is the driver, one has to think about the modification of potential as something that is not classical anymore, right? Or the multiple options for how the potential itself is modified, the dynamics of that will then force some kind of entanglement between the trajectory of the electron and the potential. So what we'll get in the full picture is entanglement between the driving field and the electron trajectory. But this could be done with a classical electron or with a quantum one principle, and this is why kind of four pictures here. And then that's indeed the basic picture we built a couple of years ago with Alexei leading this with Matan, came from the HG community classical, moved to quantum with a bunch more people with Oren Cohen, with Nick Vela, who's now in Cornell. And now let me tell you a little bit more about this, because I think it's kind of a fundamental method. In a sense, what we normally do in this process is calculate the dynamics of those electrons, get a dipole. The dipole is created by the motion of that electron, and stick it in with this formula that gives us energy spectrum. What we should do instead is understand that this dipole is created by an electric field driving everything, but that electric field should not be thought of anymore as a classical field. We have a driver quantum. Instead, let's replace this by some arbitrary state of light. And we could do this by asking, well, quantum states of light, mixed states as well, could be written in multiple ways using coherent state as the basis. This is called generalized Glauber decomposition. And there is a P function for every quantum state, Q or O mixed, that is basically using a base of coherent states. Following this procedure lets us get back to a bunch of different, basically one would need to calculate individual dipoles for different coherent states and simulate with the same tools that are currently used for ion generation simulation, multiple field strength, and then combine them together in order to calculate the energy spectrum. Or we can then continue and calculate more higher order properties, correlations, and other things about light as well. So this is like step one in order to ask what quantum statistics would do to light state. And it was actually the debate that started this is that Paul Kirkham and other people were assuming that quantum statistics is not supposed to modify harmonic generation so much. Talk about why. But what we found by doing this theory that it does matters a lot. Fox state and coherent state behave quite similar, but the right squeeze vacuum state, a little bit, is actually changing the spectrum of harmonic generation substantially. Even thermal light doesn't feel very quantum. It's actually already doing quite a lot. It's not that clear how to make short pulses, intense parts of thermal light, but it is something that will already change things quite a bit. We followed beyond this. We talked about what happens to the cutoff, right? There is typically a place where it stops. This is a famous result from Levenstein from the early 90s that was talking about what would be the cutoff. There is this 3.17. Anyone from the community is used to looking at that. That's the edge where the harmonics stop. And we found that changes. It's pretty elegant how you can actually find a new cutoff that depends on quantum. And I'll say one last thing about this is, we also asked, and this is already a later work that Nathan led, about what happens to the quantum statistics of potentially solid states of the harmonics themselves. The one would like to do the region factor representation. Nathan saw that there is squeezing created on the harmonics themselves. It's kind of inherited from driving lights moved into the harmonics. And the frontier of research right now is actually looking into doing experiments for this. I'll get to this in a couple of slides. Okay, and with this, I think I covered much of what's done on theory background, and I think it's worth asking. Well, and this was kind of people were surprised by this until about a year ago, whether we can even create lights that's quantum and intent. But somehow there is a phase transition in our minds that now everyone is considering it as if it's a trivial thing. But so actually, what's done in order to get to bright quantum lights? So if you want to, what's the most common method to create a quantum light that's not bright? For entangled pairs, typically we look at those hydrogen crystals. Right, we send light through and we can get pairs of photons, basically photons split in two, and they have correlations between them and even entanglement. There is a special version of this where we change the crystal angle and phase matching condition, so the two output photons will be going along the same axis and same mode. This is called single mode squeezing versus two mode squeezing. Single mode squeezing is kind of the simplest version of creating quantum light, because it's just one mode going out once we build the original, right? And the pioneer there is Maria Chekhova. He was actually working in Erlangen also with love, and this is like a group that was pursuing this for years before the more recent times. Already back then, they showed pulses of bright-field vacuum. And so basically, you drive this with a strong pulse, you get a strong pulse applied on the microjoule level. Right? So you can estimate the number, but this is like 10 to 13 photons, maybe 14. But in terms of picosecond regime, they pushed it further. In 2024, this is a point in time where we already partially motivated by experiments going to high harmonic generation based on the predictions we were making. They got, and this is currently the record. This is like a 25 femtosecond pulse on the microjoule level. This already weighs into the regime where you can drive non-perturbative nonlinearities with it. And this is where what's got kind of people into this phase transition regime. By now we have 3 beam lines of bright-field vacuum in Technion, in Israel, 2 in Technion, 1 in Weizmann that we built for different experiments. The first one that was in Erlangen, Maria Chekhova. We are also involved in some of the experiments there. I'll mention a few of them. They're now happening in different places around the world. So basically, we got into this regime of strong field quantum optics. And I'll tell you a little bit about experiments happening there. In the first milestone event, this is our experiment with Maria, led by Andre, a student, done in Erlangen. It's here from Technion. Is the first example of high harmonic generation driven by bright-field vacuum based on the parameters that I just showed. And I think the first example of this was showing is that this, by the way, driving harmonic generation in solids. Solids are known for reaching into somewhat lower harmonics, 7, 9, some of the results they were showing, but but not demanding more than hundreds of nanojoules of energy, just more achievable with current bright-field vacuum. The most interesting and surprising result here is that we could get, if you ask what is actually the response to the harmonics as a function of a pump intensity, you typically see an increase, and people do see some saturation at higher intensities, but it was until now impossible to actually look beyond a little bit of saturation and see this regime, because materials get destroyed at that range. It is actually not clear to us why, but what we find is that we can explore further into higher damage regimes using quantum light, and the reason is unclear. So this is an interesting point that is potentially an application why quantum light would be useful. But I want to stop for a moment and say something about this, because there is a big debate in the community about how quantum the light really is. I think it's a really important thing to point out to. And that kind of to also lower the level of excitement about potential. So first, if we think about Wiggins representation of light states, okay? So right, we can map the everything here is an harmonic oscillator. It's a single mode, and those are the light states we're trying to create for now. Multi-mode is that even more complex. Single mode harmonic oscillator can be mapped from just a position of infinitely many energy levels into a picture in 2D. This is what we call the Wigner function, right? There's some Gaussian that will be right at the center, will be a zero vacuum state, right? With the width of this Gaussian being the vacuum fluctuations. When you have thermal state, it will be a broader Gaussian, and the broader it is, the more intense it is. Now, if it's shifted sideways, we'll have a well-defined phase complex plane. This is the coherent state, classical light, right? That we're used to see. Squeezed light will be then something that is typically a Gaussian that's also squeezed. Squeezed vacuum, which are the states we're creating here, are ones that are centered at the center of this and stretched very strongly. There is one axis along which it is anti-squeezed, since it is much longer, and that's where we get the intensity from. So when we're talking about those 10 to the 13 photon events, those are extremely long along this axis. But they still have a phase, but actually defining phase only up to a 180 rotation. And now, if that squeezed light is really squeezed, it will be also narrower than shock noise, narrower than vacuum, along this axis. The thing that no one knows right now is whether it is actually squeezed or only anti-squeezed. It is definitely anti-squeezed. We see the effect of anti-squeezing. We see it in multiple ways now experimentally as well. But no one managed to actually prove that those states of light are actually squeezed. And that raises a really important question. It's not resolved. People say that thermal light is not really classical in the sense that one could use just multiple realizations of different states at different locations over here. If you have a laser and you put an attenuator on it, just do your experiment many times by different attenuations and collect multiple examples and then average it yourself eventually when you do post-processing and get back to that. But if our light here is not really squeezed, could we just do the same experiment by multiple realizations of classical intensities? Could I do this experiment in harmonic generation by just repeating that? And of course, if you try it classically, the Wigner function will be the same. Therefore, everything else will follow as well. So, do we get something unique in the fact that it's Maria Chekova can do that experiment? Now we can do exactly with single pulse. Single pulse is not many realizations. So, is there something that is different between the fact that a single pulse is described like that, even if it's very broad? Is it different? In some sense, is there some meaning to a Wigner function that is not squeezed, in the sense that it is, but still a pretty real Wigner function? Or is it, or will it never give us something that's different from just many realizations of classical experiments? And then it will need real squeeze. But we don't know, and it's a highly debated topic. Could we actually get classical responses like this?
Your calculations show that the classically random superposition coherent states that generates this bright anti-squeeze state also generates the high harmonics, right?
Yes. And I'll say the original theory is talking about multiple predictions, including the correlations and squeezing and other properties that cannot be achieved without pure squeezing. But the one effect that got most famous is the broadening of the spectrum is an effect that you can get by a mixed state as well.
Yeah. So then, according to standard quantum theory, you would get that from a random superposition coherent states. I don't
When
think
you average it many times,
Yeah.
it must be that the Wigner function is the same and everything else will follow. But if you do this experiment just once, do you have something extra hidden in there? But is there some, for example, the fact that we managed to look into deeper damage thresholds, it's doesn't mean that there is something extra happening over here. Or could we somehow find a way to do this in by multiple realizations? Because if we try it, we do multiple realizations, we burn the material. So something, this is a debate.
But if you have a source, and that source gives you a random intensity, such that over many averages of different random intensities, the Wigner function is what you have there, then it would be like I don't think that's a debate. I think that's
The Wigner function will be the same.
so
then
it's the same.
If the Wigner function is the same, will every experimental consequence also be the same?
Yes.
Right. So my assumption is that someone coming from the theory of quantum optics is, I think, like yours, is that yes, and I was therefore pursuing predictions beyond photon statistics, like already in the first paper. But now once experiments started going into this, including ours, we are now seeing effects, like for example, going into different time thresholds, and it raises this interesting question of could it be that the fact that it's a single pulse realization cool thing, it actually lets you see access something that the Wigner function alone cannot explain. And that's a debate that bothers me. I don't know. And I'm coming from a more kind of conservative approach to it, let's say. That in order to get something really quantum, we need real squeezing. But I'm not sure. The community is debating this right now. So just lowering the expectation, I would say many of the experiments we see right now are borderline quantum. But they do have effects of photon statistics, but then it is unclear whether this could be reproduced by averaging many classical experiments or not.
What about the scaling of this harmonic signals when you vary the power, basically width of this with intense width? Because I might expect some like quantum interference, right? Because here you're creating like superposition of different like points, right, in this Wigner distribution, right? If it's worth common, right? And then maybe if you just look at the one spectra, maybe it's kind of equally broad, but maybe if you keep track of how individual harmonic orders scales with the squeezing width you have and the squeezing width you have, I wonder whether there's any difference between this, like the purely quantum versus like classical
something in a. So in some sense, the way to look at why is it broadened so much spectrum? Because we do have tails of this really long distribution going super far away, and the system is extremely sensitive to the extreme tail here. Right? The rare events that are having the very, very long tail here are actually so intense. They create such a long tail, and they will contribute more than their fair share of probability. Right. So that again, I'm kind of attacking the attempts to get a clear quantum signature this way. But in practice, it means we can get really rare events to give a signature from the material that if we try to just push our coherent state over there, we burn the material, which is maybe a useful thing.
So I mean, the other thing is this squeeze state is being generated by coherent kind of nonlinear material through a parametric process that effectively conserves energy. So those very rare events, they're constrained by the statistics of the pump field.
Yeah.
So, they have to be, you could have just used that pump field originally and generated that state with appropriate modulation.
So let's try to describe this exactly, right? Imagine we have this pulse, and according to quantum theory, if this pulse does not yet know how much energy it has, right? Could it be that it will actually interact with the material and only decide of that amount of energy after interaction, at the point where it will no longer destroy the material and give you sometimes that event? Or is it collapsing earlier, co-interaction with the material, giving you a well-defined energy to that pulse? And then if it collapses earlier, and then it means it will destroy the material when that happens. Right. This is basically the question. The kind of question this relates to is when is the collapse happening about this pulse? Is it before it interacts, collides with material, or after? Now, anyway, I'm pestering this community about myself as well, and I'm also curious to discuss this further. And I'm happy to, just this last Friday, I was in conference in Germany, and some of the players from this world were there, and we were debating this as well. People shape their opinion; it's an interesting thing. But I'll say just some words of encouragement. And I'm happy to discuss this further because I think there is an interesting question about the Wigner function and when collapse happens that is happening here. But I'll say some encouraging things that we are moving forward with those experiments now, and we do have an experiment that just happened in Technion that does show real squeezing for the first time in slightly different conditions. So we are getting into the regime where strong field behavior also goes into squeezing. It's just way harder than than those earlier results. We hit stop. See this? Batteries running out? No, okay, it's okay. So basically, so you see that there are some of the earlier results are still not resolved, and this is pushing the community to look for more clearer, stronger signals, including us. There are interesting signals along those lines. I'll show you one of them right at the end. I'll say that direct measurements of this, for example, are just done now. This is the Kaminer group with Maria Chekova. Still on archive, I think it goes into nature physics. It shows the actual broadening spectrum for the first time. When some of those things are coming up, and this is all its own already really fantastic to see. Something about where do we see the real quantum effects? And this is right now my journey into trying to go deeper into quantum in the sense of squeezing and beyond. This is another TO paper we have done, or actually same year as the original one that started this. This is Nathan and Michael, joint student with Owen Pan. Well, the question here was a little bit different. We're looking at the process of the strong field interaction that's an interferometry type of scenario. Imagine that we don't put a lot of, and it's not with vacuum, with amplitudes, and we do an interaction of partially coherent lights and squeeze light. This is a method by which you can actually study the response and dynamics of the electron inside. So the electron dynamics inside thing for us to control. And I think in terms of time, I'll not go too deep into this. I'll just say that looking at attosecond dynamics of electrons is a much more sensitive probe of even weak quantum signatures. In this case, the quantum squeezing could be 1,000 of the full intensity of the coherent state, and it will still alter the attosecond dynamics in a very sensitive way. And this is, I think, a much more promising approach to doing this. That was actually the motivation for building the experiment in Weizmann. This is in the lab of Merit Lovich, between Nathan and Chen, who's a student. And this is the first example of an interferometric approach for this, and also of creating a Wigner function measurement of harmonics. You can basically do a variant of the chromodine measurement on the harmonics, which is a beautiful thing. It's an interesting thing that we do see squeezing relative to the original noise of the driving laser, but not below shot noise, which is very hard to do with femtosecond pulses. The Wigner-like noise response to the attosecond time scale is fascinating, and this is a beautiful thing to discuss as well. This is still quite new on archive, and I think it's one of those beautiful things that are right now at the frontier. How we do homodyne measurements on the attosecond time domain, and worth an entire talk. But I think it's better to use the last couple of minutes to try to give you a bigger picture, trying to classify what's happening in the field. Because in some sense, there are multiple types of quantum. Where is quantum coming from in the strong field domain? I think it's useful to look at it this way. In a sense, the most obvious type of quantum will come if we drive the system with quantum light. That's what we proposed, right? This is driven by quantum light, and this is the most active area nowadays. From a quantum state of the harmonics to first experiments that happen in this domain. There are some proposals and suggestions for how one could get to forbidden regimes of harmonic generation, and more and more. And I think it's including the attosecond bunching that we were just showing. There is another approach that is getting a lot of attention, and this is post-selection induced quantumness. This is whether we can drive a system in a conventional way, but actually post-select on the results. This was proposed by the Levenstein group. But actually, it first worked was even before our theory. This is Harry Sal's conflicts. This is a nature form experiment that was highly debated, still highly debated. No one knows how to reproduce or explain what happened there. It was one of the drivers for us to try to build theory. We did not manage to explain what happened there. And I still think it is a job for theory to manage to understand these kind of experiments. There is a lot more to say here, and plenty more papers along this line. About how one could use post-selection to try to create complements there. I'll say briefly that what the Harvey-Stiles experiment saw is post-selecting on harmonics, and then looking at the driving light and seeing very strong modulations on the original intensity of the driver, leading them to make a claim for a creation of the macroscopic cat state. This is the most quantum stream, really fascinating signature seen in the domain. And is not a consensus whether it's real fact or a wrong one. There are many debates about this. and by many follow-ups since. There are multiple tens of papers by that group and a few others doing follow-ups on this experimental and theory. So there are many things for us to figure out. There are many groups that join me into this. There is a beautiful lecture photonics from Ottawa, and Giulio Vampa, who was looking into like the combination of classical light and quantum light into creation of harmonic generation. There is a very important paper looking at coincidence measurements on non-distributed nonlinearities, G2, G3 type effects. This is 100 energy pairs. And there are multiple others. There are our collaboration. You can look into more. There are more groups joining into this, even like since my talk last year. So it's getting quite interesting. And I'll say a few words to finish, but I think are useful for future directions. Yes, there is. I left some space here on purpose. I think the area that we will see most exciting moving forward is what happens when the quantumness is actually coming from the material. If you think about it, if we drive a gas that is held in some way where correlations is created inside, or solids, of course, like there are so many many-body condensed matter systems that one could drive and decide, and already people study some of those with strong field driving. Anyway, it's worth an entire talk. We were doing this earlier paper, also 2023, asking what happens when there is a correlated many-body matter, based on the same theory we built back then, with additional computations on top. What happens when you have a correlated system of electrons, and the result that is expected is that you actually get this imprinted on harmonics. The part that was really not trivial to understand how do you really learn from correlations on harmonics, coincidence between different harmonics, for example, what was the quantum state of the material? I think as a quantum spectroscopy tool, there is a lot more to do here. There are multiple papers since, and this is on the theory front getting the most attention right now. And I think it's really interesting to consider. And I'll tell you about one piece of experiment there. I think I'll skip this. This is the work by Andrea Pisi, who's now in Cambridge, and the let's say student where we did this. I think there is a fourth path. This is actually, do we need quantumness to arise from any reason, or can we actually just rely on the nonlinear interaction intrinsically, like QED alone? And this is the path that I would say Jameson took, in this really beautiful work. But the question was, in some sense, we know that you can get combinations of photons summing up, give a second harmonic, but then the opposite of this will be splitting to give us entangled pairs. So could we say that we have creation of harmonics to create pairs harmonics, get them in that sense entanglement between pairs of EUV photons? And what Jameson found, and I think it's really important, is that when those are created, they're created in particular angles that phase mesh and are different from the original emission of harmonic generation. And that the numbers are not so bad for millijoule pulses used for harmonic generation. One would still get hundreds to a few thousands of photons per event. Also spread over a wide range of frequencies. So thinking about the right experiment would not be super easy, but it's definitely within range to look into entangled pairs of EUV photons. And in some sense, it's mostly universal effect because it does not rely on the flow material or driving this quantum or any of the other effects we were thinking about. And I would say back into this domain and the promise of squeezing, and I'll finish with this one. This is Igor Anisim, one of our newer students. He's a joint student with Michael Kruger, and this is done in Michael Kruger's lab, where we built a homodyne system for a non-perturbative nonlinearity. This is driven by classical light and asking what's the non-perturbative nature of the nonlinearity. This is AOPG. AOPG is aligned graphene sheets. And they're known for behaving in a very non-perturbative manner already third harmonic. So we have two variations of third harmonics here. One is a reference, local oscillator, and one in the non-perturbative manner. And there is a signature of squeezing that's created here, despite operation in attosecond dense pulse regime. And real squeezing, this is still being analyzed. And the beautiful thing here is that we now understand that this is a collaboration also with the theory team, and Amisha even on part of the theory with the student imply that the racon and the lack of gap of graphene is actually responsible for creation of squeezing. Discuss why. I think it's one of the beautiful effects that are happening over there. I think with this, I'll wrap up. I'll give you just kind of the way I think about this field nowadays. That quantumness is a norm to control light emission, both the classical and quantum properties of it. It's especially sensitive. We look at the attosecond dynamics inside. There is an interest in understanding what type of quantum states we can engineer in some sense, and then as a probe for diagnosis of quantum states matter, especially valuable. Can look more at those papers are the ones that we're discussing today. There are theoretical ones and experimental ones, and the most recent ones on archive. I'm happy to follow up. That's everything I wanted to tell you today. I'm happy to follow up while I'm here. Thank you very much.
So initially, when we go faculty area growth in atto-science.
Thanks, Ida. Can you talk a little bit about like the multimode case? Primarily when, in like a very short pulse, I'll have many longitudinal modes.
So if we think about beyond one mode, then of course the quantum state is no longer, it's not just a Wigner function, so called, right? It's not easy to plot it like this. From an experimental perspective, it's actually easier to create multimode. We're fighting quite hard to make a Chi2 crystal giving us just one mode your way. The problem with the multimode, if you don't design it well, is that you very quickly go into a kind of large number statistics theory. You just sum up many photon statistics and you get a Gaussian again, but everything goes back to a Gaussian or Poissonian distribution. But I'm sure that if we design it carefully, we'll find something interesting, like two mode squeezing that are somehow interacting on the same sample will give us some. I don't know. There should be something more ambitious to do there. We don't have the intuition for how to design experiments like this yet, even on the two mode level.
Can you say again what you're saying about the squeezed Wigner function and like whether there was an experiment that could detect like a difference between like a mixture and
So
I guess like a mixture of like squeezed.
So let's imagine we have those those elongated Wigner functions, for example.
Yeah.
Right, which you could make up of multiple smaller Gaussians that are each of them is just a regular coherent state.
Yeah.
Right. So from the Wigner functions, if I just want to create a Wigner function, I can just repeat classically experiment with multiple intensities and phases for the classical, right? So I reproduce the same Wigner function. Now, let's say I use that original Wigner function that I created to drive some process, or I repeat classically that experiment with multiple coherent states, right? Drive that process. In some sense, to understand whether I can do something unique that without just repeating this multiple times, what I want to understand is whether there was a collapse of that original Wigner function to a particular coherent state before it arrived at the interaction point, and then it means there is basically no difference, just like repeating this multiple coherence experiment without knowing which one I do at the time, or whether it will only collapse after interacting with the sample, and then it will actually potentially give me something more unique that I can know.
A foundations question or something like surely like if you like went through the calculation you would show that like in either interpretation of like collapse before or after the predictions for the result of any experiment would be the same. So like what is I'm not understanding like what is the experimental like discrimination between these two cases.
So for example, if you have a Wigner function that is squeezed,
Yeah.
because it's narrow enough, then you cannot build it as a mixed state of coherent states. Right?
Sure. So like
That one
if you
you
actually have like a different Wigner function which is like has negativity or something, then like you can get some of
for
it.
example, right? Those ones which we cannot build by a sum of Gaussian states. You would say, oh, this one definitely only collapses after the experiment. But you have scenarios where you have a Wigner function that you can build from a sum of Gaussian states. So it is Gaussian, right, as well, and it's even not squeezed, so worse than Gaussian. In terms of how interesting it is, and that still is actually the entire thing in advance arriving and only collapsing after, or is the fact that it is a non-squeezed Gaussian state already proving that it can be, must be collapsing before. I think that's the kind of, maybe that's a better phrasing question.
Are you asking for something which is like non-linear in the density matrix? So like, how can this happen if you're just like asking for an observer?
I mean, the interaction will be, let's say, very non-linear in the density matrix, maybe the same, right? This is for us. Oh, okay, non-linear, not in the sense of,
Not in the
it is still showing the equation and still limit light if you want. That will be linear, yes, but interaction will be a non-perturbative.
I mean, okay.
Yes,
I don't see how that changes anything, but like.
yeah, you're saying it should not matter to be in any sense because it's just a linear. The quantum mechanics is linear, and therefore,
Which is, I think the point is, I guess, maybe like fundamentally, there's no way to distinguish between those two ways of preparing that state.
Yeah.
So whether you produce a bright squeeze vacuum, which then, let's say you send through a 50% attenuator, so that it's broadened, so that
yeah,
so that state on the output, you can't distinguish between, like you have no way of figuring out how that state is. It could have been prepared by a squeezer, or it could have been prepared by some pulse source that randomizes the points. Yeah.
without going through any squeezer.
Yeah.
in-
So I think what you're saying is like, according to standard quantum mechanics, we can't distinguish between
Yeah.
those two emission kits. I think
Like,
my understanding is that as well, so I'd like to actually understand a bit better the case you were describing.
the damage threshold as well. Yeah, so basically the quantum mechanics I know is like yours. The fact that Masha Kefova, as an example, is now arguing to the contrary, but well, she was the one teaching me quantum optics, is making me more hesitant and more curious.
So I actually, maybe I can, so not related to foundations, but sort of from a very practical point of view, I like to think about sort of quantum advantages. And so like this state here is one where you have this big variation in the intensity, right? And so the question is how I can generate that. You know, one way I can generate that is have like a nonlinear system that I send coherent light into, and it generates like solid functions, right? So you get like a mode loss system where you end up with very short pulses that have large intensity. And so my input is the CW laser. On the output, I have pulses with large intensity. I can send that into my high-harmonic generation and get some HHG. Or I can send it into something squeeze-ly. And you can think of squeeze light as something that if you plot the intensity in time, the intensity is fluctuating quite a lot. I guess that's what this means. So in time it has this very wide variance, but it's sort of not controlled in the same way as in the mode lock system. So what I'm trying to understand is it better if I have a CW laser to send it into a mode lock to a system that does mode locking? It's a very efficient thing to short pulses with large peak intensity, or is it better to send it into a squeezer where I have this kind of random intensity fluctuations where at some points it's going to get very high intensity? That A to B comparison, just practically that seems important.
So you're saying it could be that the squeezer is actually as efficient as the modulo or amplifier.
Yeah, I think it's just like if you have like, let's say my resource is a laser that has this much CW power, how much HHG can I get if I have a good mode locking system versus like a squeezer?
So we were actually designing the original experiments. Eventually did it with Melania for many reasons, but we thought we'll just try to create thermal lights. It's very intense. But in a sense, this is supposed to be the easiest version of it, which is kind of also the least, will not create a controversy. It will be very clear that it's very not quantum in some sense. It will still show us the broadening thermal. That's what we wanted to show first. Then we were actually looking for the right way to create very intense thermal lights. It's not super easy. There are types of amplifiers that we would like to drive with a compensation pulse with no C. So you'll not actually amplify anything. And this is probably kind of the way to doing this, right? In some sense, a bright squeeze vacuum is not very far from that, right? It's although it should have some squeezing. But why are we all arguing that there should be no squeezing? For those okay, because of course, if you have 10 to 13 photons in the state and you lose, I don't know, 50 of them, it's kind of likely because the number of photons is so high, then we're very quickly lose squeeze. Right? For context, although not all of it, one could calculate. So the part of the debate is that people still believe that there is a good chance that there will be squeeze in terms of 13. Maybe 0.01 dB. Maybe that's worth something, right? Because it cannot be made from just a sum of mixed states, right? So we don't need more than 0.01 dB to make a plane. I don't know. I like the fact that
Any other questions? Okay, so I think this debate will continue and is here for a while, so we'll keep debating, so thanks everyone.